which is at the basis of Scott's continuous semantics, and it's the intuition that we have in mind. Why do I say that computing least fixed points allows to model recursion? Well, because if you take a function, for instance, here, we have a function that takes a function f as input, a natural number n, and then if n is equal to 0, then it gives 1, otherwise it multiplies the result of applying the function to n minus 1 times n. So this function is not recursive because it takes the function f as input and it applies f here. But if you take the least fixed point of this function, it gives you the usual factorial. And this is actually corresponding to the recursive definition of the factorial. Okay, so the theory of program approximation has been first developed in the setting of untyped lambda-calculus. So I recall you that in this setting we have terms that can be either variables or lambda structures or application. So the basic notion that we take here is the notion of function as a primitive object. And then the computation becomes substitution, because a function that takes x in input and gives n as a result, when we apply it to n, reduces to the term n, where all occurrences of x are substituted by n. So, thanks to using Scott's continuity, Scott was able to define the first denotational model of lambda-calculus, which is the infinity. This was in 1969. Some years later, Barnett proposed a more syntactic model, in which every program can be represented as a tree. So more precisely, we have the Bõhm tree semantics that represent the execution of a program as a possibly infinite label tree. And this can be seen as a syntactic model of lambda-calculus. So in order to understand this kind of semantics, first we have to look more into details and check what are the possible behaviors of a program in this calculus. And so the first behavior that we observe is the fact that the program can be normalizable. So if you have a program P that computes, and after 100 steps produces the natural number 42, then this gives a completely defined result. But then you can have a program P that reduces to a program P1, that reduces to the program P, that therefore reduces the program P1. So it continues like this indefinitely, and this gives never gives any result at all. So this is going to represent the completely undefined program. But then we have something in the middle. Terms that are called solvable and that reduce by producing some finite portion of the output, for instance this O1, but they also have a subprogram P1 that produces a finite portion of the output O2, but then there is also a subterm P2. So every time we get a little piece of output, and there is always a subprogram that continues its execution. So the execution of the program is actually infinite, but every time it gives a finite portion of the output more. So the typical example would be the program computing the number pi. It first gives 3, and then 1, and then 4, and then 1, and then 5, and then 9, and then only if you take the limit of all its computations, you can retrieve the whole number pi. Okay, so summing up, we have completely defined terms that we call the normalizable, then undefined terms, we call them solvable, and the solvable gives possibly an infinite output. And to be more precise, we can now define what is the Bõhm tree of a program P, and it is defined as follows. If P is completely undefined, so if it is unsolvable, then its Bõhm tree is bottom. Otherwise, P will give some input, and it will continue with subprograms P1, Pk. So its Bõhm tree will have this output in a node, and then we'll have, in this case, k subtrees that represent the Bõhm tree of P1 and the Bõhm tree of Pk. And then we continue. And then we say that in the Bõhm tree semantics, a program P is equal to a program P1 or P prime, if and only if the Bõhm tree of P is equal to the Bõhm tree of P prime. So now consider that this definition might look inductive, but is not. Because in what one would think it is the inductive case, we have P that reduces to an output MP1 Pk. So in the process of reduction, the size of P can increment, even exponentially. So this is not an inductive definition, but still it is well defined because it actually is a co-inductive definition. It's one of the first examples that we find in the literature of a co-inductive definition. So for instance, if we take the Bõhm tree of a fixed point combinator Y, then the Bõhm tree will be an infinite tree with lambda f dot f applied to f, applied to f, applied to f, and so on. So co-inductive objects in the 70s, when this semantics was defined, were not really well known in the scientific community. So people would be rather reassured to use an approximation theory in order to retrieve the whole infinite object by looking at all its finite pieces. So in the classic approximation theory for Bõhm trees, the idea is to consider a set A of finite approximants, where an approximant can be either a bottom or this finite piece of the output, lambda x1 xn dot y, and then A1, AK are in their turn finite approximants. So this grammar is inductive. And the idea is that the bottom represents the completely undefined programs, and of course we can also associate a preorder, which is the preorder generated by saying that bottom is smaller than any approximant A. And the idea is that bottom represents the least amount of information, so no information, and then it's smaller than any other approximant. And then we can define the set of finite approximants of a program P by taking all the pieces that, the finite pieces that come out from the computation of P. So we reduce P when we find a Q that gives enough information. We take a finite approximant of Q and we put it in the set. So for instance, if you take the completely undefined program omega, it's only approximant is the bottom because it never gives any output. And if you take the set of finite approximants of a fixed point combinator, then you can find bottom and then lambda f dot f applied to bottom and then lambda f dot f applied to F, applied to bottom, and so on. And then there is an approximation theorem stating that the Bõhm tree of a program can be actually retrieved at the soup of all its finite approximants. So for instance, the Bõhm tree of Y can be seen as bottom soup lambda ff bottom soup lambda f applied to f bottom and so on. So these are all the finite pieces, and if we perform the limit, we retrieve the whole tree. Okay, so this approach is very nice. The only little problem is that it is difficult to generalize from lambda-calculus to other programming languages of interest in the community. For instance, algebraic calculi, differential calculi, probabilistic calculi, and quantum calculi. So what all these different calculi have in common is the fact that they can all be interpreted in quantitative semantics of linear logic that are based on vectorial spaces. So the origin of all these semantics is in a paper by Girard called the Normal Functor Power Series and the Lambda Calculus, appeared in 1988, where, and if you look in this paper, at a certain point, you will see that Girard makes a remark. He says that a notion of differentiation is available in these models, but it doesn't really do anything with it. It just remarks that derivative is there. And this is a good news because in mathematical analysis, one uses the derivative of a function in order to infer properties of the function itself. The derivative measures the way the function varies when its input varies. And moreover, one can reconstruct the function, or better, one can expand the function, develop the function into an infinite power series by computing all its nth derivative in a point. And this is the Taylor expansion of a function. So there are many standard mathematical tools that are at hand when we do differentiation. The question is it possible to use this kind of tools when speaking about the theory, or studying the theory of programming languages? And the answer is yes, if we understand what does it mean to derivate a program. So this is what Erard and Renier did in 2003 while introducing the differential lambda calculus. The idea was to take Girard's remarks seriously and exploiting the fact that in the model of lambda calculus we can find derivative to understand what does it mean to have a syntactic derivative operator. So in the differential lambda calculus, one can derive a function lambda x dot m and apply this to a term n. And what does it mean to derive a program and apply it to another program? It means that the program lambda x dot m can only use its argument linearly. So when we do the reduction, we have n that is substituted linearly for exactly one occurrence of x in n. And then, if once we have enriched the syntax of lambda calculus with derivatives, we can actually perform the Taylor expansion of a program. And the idea is to develop the application of a program to an argument x by taking an infinite power series of linear applications of the program to x, and then a classic application to 0. And then we have a coefficient that I'm not going to discuss today. But this is interesting, and the ambitious goal here is to replace the theory of program approximation, which is classically based on continuity and Bõhm trees, with this newer theory of resource consumption that is based on the Taylor expansion. Okay, for our purposes, we don't really need to understand what this numerical coefficient is. And nowadays, the target language of the Taylor expansion is actually often presented as a resource calculus, whose syntax is more or less as the usual lambda-calculus. So you have a term, which is either a variable, or a lambda struction, or an application. But in the case of an application, you cannot apply a term to another term. You need to apply a term to a bag. And what is a bag? A bag is a multiset of terms. And the idea is that each term in the multiset is available exactly once. You cannot erase or duplicate the resources in the bag. So how does reduction goes? Well, consider, I'm going to introduce it in an example. So consider a term lambda x dot t, which is applied to a bag having 3 resources inside, S1, S2, and S3. What should be the reduct of this? Well, that depends on how many occurrences of x there are in T. Assume that T has exactly 3 occurrences of x. In this case, we are going to substitute S1, S2, S3 for the 3 occurrences of x. So S1, for instance, goes here, S2 goes here, and S3 goes there. The problem is that in a multiset, there is no ordering between the elements, so it does not make any sense to choose one particular occurrence for S1 and another one for S2 and another one for S3, because there is no way to choose. The only thing we can do is take all possibilities. So actually, we need to have a third category in this calculus, which is the category of finite sums. You can intuitively see these sums as an inner choice between programs, so a non-deterministic sum, but in the reduction you never actually perform the choice. All the sums will be there at the end. So we consider all possibilities. We put S1, S2, S3 in these 3 occurrences in all possible ways. But what happens if we only have 2 occurrences of x in T? Well, in this case, there is no way that this function can use each of its arguments exactly once. And in this case, the program raises an exception that destroys the whole program, and the result will be 0. And this happens if we have less occurrences or more occurrences of x with respect to the cardinality of the bag. Okay, so let's do some examples. I will call I the identity. the first remark that we can do is that the linear fragment of lambda-calculus can be embedded in this system. So in the linear lambda-calculus, you only have one occurrence of every abstracted variable. And every abstracted variable must occur exactly once. So in this example, you have lambda x, y, z dot x applied to a back y applied to back z. And then we have three applications of the identity. So by contracting the first radix, we have this I that goes in head position and give this. And then this is the identity applied to y, so y goes in head position. And then we have the second bag with the identity that is substituted for y, and then I gets in head position again, and then this identity is to z, and it just gives identity applied to identity, and this reduces the identity. So this is an easy example because the lambda term is linear. But you can also have resource terms with more occurrences of x, for instance. Lambda x dot x applied to a bag that contains x. So to have a no-zero reduction, we need to give this function two arguments. Let's try to give this function twice. Well, in this case, the first argument in the bag is substituted for the first variable, the second for the second, and since they are equal, it's not interesting to choose an order, and this just gives lambda x dot xx applied to itself. But now, there are two occurrences of x here. And here I have a bag with only one program inside. And this goes to 0 because I cannot substitute this one in both occurrences. So resource terms may experience starvation, we can say, but they may also experience starvate. Here I have a term that uses x once and y 0 times. What happens if I apply to two bags with one resource? Well, the first reduction is going to be fine because this I is going to be substituted for this x. But then I have this I that should be substituted for the new abstracted variable, and this is impossible. And therefore, this goes to 0. So to have a no-zero reduction, you really need to have in the bag exactly the number of occurrences that you need. So here we do apply lambda x dot xx to a bag with y and z. And so here we will have two possible results. Y goes in the first position or in the second position, and similarly for z. So you can also see that non-determinism may arise along the reduction. I start from something which is a single term, and I obtain a sum of terms. Okay, so I'm not asking you to become familiar with this calculus on the fly. What I'm asking you is to remember its main properties. So when we have a reduction of a program of shape lambda x dot t applied to a bag s1, sn, this gives a result which is different from 0 if t uses each of the s1, sn exactly once in the reduction to a bag. Moreover, if t reduces to a context with some 0 inside, then the whole thing goes to 0. This 0 is like when you raise an exception, that the exception goes up, up, and up, and it destroys the whole program. And then the main properties enjoyed by the calculus are strong normalization, confluence, and linearity. Notice that strong normalization is trivial because here there is no duplication that it is involved. The confluence is easy to check because it's a locally confluent language and enjoys strong normalization. So one just applies Newman's lemma. And then the linearity states that nothing gets erased in a no-zero reduction sequence. Okay, so now that we have the target language of the Taylor expansion, we can actually define what it is the Taylor expansion of a lambda term. So since I'm considering an idempotent sum, because I don't want to enter into the details of the coefficients, we can consider the Taylor expansion as something taking a lambda term and giving a set of resource approximants. So the Taylor expansion of x is the singleton x. The Taylor expansion of lambda xm is just the set of resource terms lambda x dot t, where t is a Taylor approximant of m. So the interesting part is the Taylor expansion of an application. In the set that is associated, we can find resource terms whose shape is an application, where T is a Taylor approximant of M, S1, Sk are Taylor approximant of N, and how many are they? Well, a priori, we do not know how many times M is going to use its argument N, and so we take all possibilities. So we take the union for k in the natural numbers of all the possibilities. Okay, here's some examples. The Taylor expansion of the identity. If you have a subterm occurring in the right position of an application, you need to consider all possibilities. Here we have the Taylor expansion of omega. And omega is delta delta, so we can see the Taylor expansion of delta here and the Taylor expansion of delta there. But here we have an extra level. So in the bag, we need to consider all possible numbers of resources and so on. So if you look at the Taylor expansion of a term, you can see that the structure of the expansion is very similar to the structure of the original term. And this is clear because this definition is inductive. Okay, so in the Taylor expansion, we still have radixes. Okay, if a radix was in the original term, there exist terms in Taylor expansion that still contain radixes. So the Taylor expansion is a static operation, but we can endow it with a dynamic behavior. And the idea is that since the calculus is strongly normalizable, then we can compute the normal form of the Taylor expansion just by normalizing all its elements and then taking the U. So if we normalize the previous examples, in the case of identity and delta, they are already in normal form. And the Taylor expansion of omega is the empty set because it is an unsolvable term. And actually, this is the case for all unsolvables. And then if you look at the normal form of the Taylor expansion of a fixed point operator, then you can see that this is very similar to the set of its finite approximants, except that we have some replication due to the resources. Okay.
Excuse me, can I ask something?
Yeah, sure.
When you write the normal form of t on the right-hand side in the equation on the top, the normal form of t is a sum of terms, right?
Yeah, sure. So yeah, in our case, it's a set of terms, and that's why we take the union.
So the normal form of terms is the normal form of terms, sorry, is a sum of terms. So you consider it as a set, and you take the union of all of these.
Yeah, exactly. So you flap them.
Okay, thank you.
And moreover, it's a finite set. So for a resource term, its normal form will be a finite sum. And in this set, you take all the elements of the sum. Okay. So now we have two ways of approximating a program. The first one is the classical one. We compute its Bõhm tree. And the second one is to first compute its Taylor expansion and then normalize it. If we take the Taylor expansion, we have some advantages. In particular, the fact that the Taylor approximants are closed under application, which is a property that is not enjoyed by finite approximants of Bõhm trees. Moreover, we can use strong normalization, confluence, and linearity. And another advantage is that this approach does generalize to the mainstream languages that I have discussed above. And of course, there are also disadvantages since you are considering this linearization, and every time you're taking all possible choices for your resources, you will have a lot of indices that arise because of the linearization. Okay, and now we can ask what is the comparison between these two approaches. We have seen that the normal form of Taylor expansion of a program looks very similar to its set of finite approximants. And in fact, Erard and Renier proved that there is a commutation theorem stating that the normal form of the Taylor expansion is equal to first computing the Bõhm tree and then computing the Taylor expansion of the tree. So this approach, as I said, has generalized to many languages, and in fact, if you look at the recent literature, you can find that many papers have a similar structure. They first define a source language and then a target language, which is some variation of the resource calculus, and there is a proof that it enjoys confluence, strong normalization. Then they define the Taylor expansion, they do the static analysis, the dynamic analysis, and then sometimes we also find an adequacy. And there is also a generalization of a commutation theorem that I already mentioned. What we found a little disappointing was the fact that from this kind of results, there were no study of the consequences of these results. And this is strange because as a direct corollary of this commutation theorem, you get that two programs are equivalent in the Bõhm tree semantics, if and only if they are equivalent in Taylor semantics. So one should imagine that there are also theorems to prove. So in collaboration with my PhD student, Davide Barbarossa, we decided to explore the real power of the Taylor expansion. And we started with a bunch of fundamental theorems in lambda-calculus. So this, if you put them all together, basically you find the whole chapter 14 in Barendek's book. And so we started from the contextuality of Bõhm trees and its vericity lemma that usually follow from Scott's continuity via a topological argument. And then we analyzed the perpendicular lines lemma that has as a consequence the fact that the parallel law is not lambda definable. And the perpendicular lines lemma is a consequence of Kahn and Plotkin sequentiality, and the non-existence of parallel law can also be seen as a corollary of the stability. So this is the picture of the classic results in lambda-calculus. What we prove is that using this commutation theorem, you can actually find easier proof of the contextuality of Bõhm trees and the genericity lemma. And also we were able to prove Scott continuity. So this is not really surprising in the sense that there was a common belief in the community of the fact that the commutation theorem for Taylor expansion were more or less the same as Scott continuity. What we found more surprising was first the fact that these proofs are really simple. So the notions that are used in the proof are simple. And then the fact that from this commutation theorem, we were also able to prove the restabilities and the perpendicular lines lemma. And this is remarkable because not only gives alternative and simple proofs, but also shows that all these results are independent. So I'm saying that these proofs are easier, so now I feel obligated to give you some concrete examples, not the whole proof, but at least to explain the structure of some proofs. Let's take the contextuality of Bõhm trees. So the statement says that if two programs have the same Bõhm tree, then whenever you plug them in the same context, also the result will have the same Bõhm tree. So this is a fundamental property that it is enjoyed by Bõhm trees. Since the equality on Bõhm trees is equivalent to having the same normal form of the Taylor expansion, then we can just assume that the normal form of the Taylor expansion of M coincides with normal form of the Taylor expansion of M. And this is what we have to prove. Do you see the pointer?
Yes.
Okay. So what is incredible is that we can prove this by structural induction on the context C, which is impossible to do for Bõhm trees because then you have the dynamic behavior of the Bõhm tree which is involved. And the only difficult case is the application. So consider the case where C is a C1 applied to a C2. Well, then I have to take something in the normal form of the Taylor expansion of M and prove that it is in the normal form of I have to take something in the normal form of the Taylor expansion of C of M, and I have to prove that it is also in C of M. And since this gives one side of the inequality, we get the other side by symmetry. So we take this T. What does it mean? That T belongs to the normal form of the Taylor expansion of C of M. Well, it means that there exists a T prime in the Taylor expansion of C of M that generates this T. But if it is in the Taylor expansion of C of M and C is an application, then it will actually have be in the Taylor expansion of a C1 of M applied to a C2 of M. And so we will have a T prime that has the shape of an application, where the S1 belongs to the Taylor expansion of C1 of M, and the U1 UK belongs to the Taylor expansion of C2 of M. Okay, so T prime has this shape, And starting from this, we can normalize because we have strong normalization and get this t plus something. Okay, and now we can use strong normalization and confluence to say that since we can choose what strategy to use, we can first normalize S1, U1, and UK, and then we will find the same result. So I can factorize this reduction like this.
Sorry,
Yeah.
how do you know that the t plus the capital T is not a zero?
It's not
It's not a zero. It's not a class. I mean, you could have the U1 to UK more or less times that what S1 expect, and then you get zero, not a t plus t.
Okay, why is it's not zero? Well, because so the hypothesis is that T belongs to the normal form of the Taylor expansion of C of M. This means that C of M is non-empty.
Okay.
So
Okay.
you start from this T and
Yeah,
you
okay.
find the term that generates this T.
Yeah, okay, I see.
You look at the shape and then you first normalize the component and then you normalize the whole. And here you notice that this normal form of S1 is in the normal form of the Taylor expansion of C1 of M, because because S1 was in the Taylor expansion of C1 of M, and this is normal. And similarly for the U1 UK. They are in the normal form of the Taylor expansion of C2 of M, but that's where I can apply the induction hypothesis. This, I know, is the same thing as the normal form of the Taylor function of C1 of n, and similarly for the U1 UK. And then we conclude that T is also in the normal form of the Taylor expansion of Cn. Okay, so on the one side you see these indices that arise, but on the other side, what did we use it? Just strong normalization, confluence, and induction hypothesis. Okay, so I don't know how much time do I have left.
It's okay. You can finish, I think. I mean, you have 4 more slides, so go ahead.
Yeah, okay. Okay, so the idea is that these Taylor approximants are just like Bõhm tree approximants can be formalized by defining linearized and affined resource terms. So a resource term is linearized if every bag in the term has cardinality 1. And it's affined if it has cardinality at most 1, so 0 or 1. So the idea is that if you have an affined resource term, then you can just associate it with an approximant by substituting the bottom substituting the empty bag with bottom and getting rid of the multisets. Why? Because in a multiset you will always find something. If you find nothing, you put bottom. And similarly, every approximant of a Bõhm tree, which is different from bottom, can be sent into an affined resource term by stating that bottom becomes the empty multiset. Okay, and then you can prove that if you have an approximant different from bottom, then you can translate it and translate it back, and you will find the original term. And similarly for an affine term, you can translate it and translate it back and find an approximant. And then there is this property that says that if there is a linearized T in the normal form of the Taylor expansion of n, then n is beta normalizable. And if it is beta normalizable, you can find such term. So in fact, the normal form of the program is given by looking at the structure of the corresponding resource term. Okay, so another result that we were able to prove is the genericity lemma that states that if a term M is unsolvable, then if C of M has a beta normal form, then it must be constant. So C of n is equal to C of n for all n. What does it mean? It means that if a context applied to an unsolvable term can give a beta normal form, then it's not using this unsolvable at all. And then you can put whatever you want in the whole of the context, and the result will be constant. So there are many proofs in the literature, topological proofs and syntactic proofs. In our case, we can redo a proof more or less as before. So assume that C of M is normalizable, then there exists a linearized term in the normal form of its Taylor expansion. And so let's and the associated program is actually the normal form of C of M. So what does it mean to be in the normal form of the Taylor expansion? It means that there is a T prime in the Taylor expansion that generates this T. And so here we can split the T in a part deriving from the context that I call small c, and the part deriving from the term. So now that they're split into parts, we can first normalize the S1 Sk, and by confluence we still get our result. So here, once again, we are applying confluence and strong normalization. But now we know that the Taylor expansion of M is empty, because the normal form of the Taylor expansion of M is empty because M is unsolvable. And so if I normalize something that I find in the Taylor expansion of M, the result will be 0. But remember, if I have a context with 0 inside, everything is 0. So the only possibility to have this reduction to a non-empty result is that the whole does not occur in the context in the first place. And then, of course, you can substitute for the whole whatever you want and still find the same result. And this allow us to conclude. So once again, you see that maybe the proof is not very easy to follow, but the arguments that are used are very simple. Confluence and strong normalization of the calculus. Okay, so I'm not giving more details of proofs. If you're interested in just look at the paper, but I do want to give you an idea of the perpendicular lines lemma. This is going to take me 5 more minutes, if possible. So what does this statement says? It says that if you have a context that has n holes inside, so this means that you can see it as a function that takes n lambda terms in input and it gives one lambda term back. So if this context seen as a function is constant on n perpendicular lines, then it must be constant everywhere. So first, what is a line in lambda calculus? Well, a line is the analog of a line in, say, the Euclidean space. In the Euclidean space, a line is a set of triples where you fix 2 components and you let one component vary. And so 2 lines are perpendicular if you take a different component that varies. And so this a line in lambda calculus has the same principle. You take, for instance, in lambda 3, you take triples of lambda terms, and you have only one component that varies in the three perpendicular lines. So this perpendicular lines lemma is known to hold for Bõhm trees. This is proved in Barendrek's book using Kahn and Plotkin sequentiality. And then it also holds in lambda beta. This was proved by De Fryer and Androulis in 2008 using reduction under substitution property. And then there is, if you only consider the closed term model, then there is a counterexample for lambda beta that was found by Barendrek and Plotkin using Barendrek and Statman using Plotkin's terms. It is unknown whether the PLL holds in the closed term models of Bõhm trees. So if you look at the statement, it means that if you have a program that takes in input n programs, and you make one component of the argument vary at a time, you find every time a constant function, then it means that the constant does not use any of its argument uniformly. So if a constant is if a context is constant on n perpendicular lines, then it must be constant everywhere. So if you consider the theory of Bõhm trees, what does it mean? That a context is constant in Bõhm trees. It can be constant for several reasons. The first reason, the hole where you place your argument is not contained in the context at all. So this is the trivial case. It is constant because it does not have a hole inside. But then you can also have the hole that is erased during the reduction. So it is there in C, but then when you reduce it, the hole is erased. Or you can have the hole which is hidden behind an unsolvable. So you don't, it is there, but you don't see it because the unsolvable destroys the hole. And finally, you can have the hole that is always there, but it never goes in head position. So we say that it is pushed to infinity. It is always there, but it never appears in the Bõhm tree. Okay, very good. But now, if we restate our lemma in the theory of Taylor expansion, and I recall that the two statements are equivalent, then if I take an approximant, a reverse approximant C in the Taylor expansion of my context, which gives a non-trivial result, y can be constant. Well, it cannot erase the hole during the reduction because it's linear. It cannot hide the hole behind an unsolvable because it is strongly normalizing, so there is no unsolvable. And it cannot push to infinity the hole because every term is finite. So in the Taylor expansion, a context must be constant because the hole was not there in the first place. But so we are left in the proof with a trivial case, and so we are happy about it. Moreover, so we can state the claim that every constant in the Taylor expansion of this context enjoys the following property: if its normal form is different from 0, then it cannot contain the hole. And from this, the proof follows. Moreover, our proof does not really use the fact that our programs are open. And so we can also tick the last box and say that the PLL holds also for the closed models of Bõhm trees. And this concludes my talk. So what should you take away? Well, the fact that this paper is not really about lambda calculus, but it shows in the context of lambda calculus, which is the simplest framework, some techniques that can be used to prove qualitative and quantitative properties of programs. And these techniques should easily generalize to a variety of other languages. And that concludes my talk.
Okay, thank you. Okay, if somebody have any question, you can just unmute yourself and ask.
Yes, I do have a question actually. Okay, but first, thank you. I really like the talk.
You're welcome.
I think it's very interesting, the topic. So my question is mostly general one. You said that the original proof, for instance, of Bõhm tree contextuality is very, I think it's very technical one. And so you prove it composing to proofs, and the part that you showed is easy, but I wonder if the other part is also easy. I mean, the commutation proof of.
So the point is that it's not as difficult as it appears in Erard and Regnier's original paper. So,
So you know what, relatively simple proof.
It's relatively simple in the sense that one needs to check a commutation between the normal form and the Taylor expansion, and once you have this, you get the result. So in the paper, we also give a sketch of a simple proof of this fact. Of course, there are some little imprecision because it's just something that was already known so the idea was really to show all the ideas of the proof, maybe omitting some little detail. And the conclusion is not trivial because there is some work to be done there, but it's not particularly difficult at all.
Okay. And one more question. I think that sometimes the labels are used to prove these kinds of properties about Bõhm trees.
Yeah.
So I wonder if some other properties that are usually proved using Levy labels could be proved using these kinds of techniques. Maybe you can.
Yeah, I think so. I don't know what other properties are used for the
finite family developments and this kind of.
So the point is that you can think about Wadsworth and the label system as a dual approach. In their approach, they put energy on the left-hand side of a retex in some sense. So you have the lambda structure that has a certain energy annotated, and once you contract the reduct, the energy goes lower. While here we are giving the energy to the arguments. So it's the argument that cannot be duplicated or erased. So it's a dual approach. The fact is, so the beauty of our approach with respect to the V would not agree probably, is the fact that behind the reverse calculus there is a clear logical system, which is the differential linear logic. While the idea of by Wadsworth and Levy was let's try to put all indices everywhere and ensure that the calculus does normalize, but without a clear theory behind.
Okay, thank you for your insightful answer.
You're welcome.
Okay, I have a couple of questions, but more for the resource calculus than your result. But since you are familiar with it, so you mentioned at the beginning when you showed all the family of lambda calculi, that you can encode or you can consider vector spaces to understand them. But how? I mean, for me, the resource calculus, the sum in the resource calculus is not a sum in a vector space. Well, you don't have scalars from the beginning, and then every term in the sum they don't interact with each other. It's just like it's really a multiset. It's not a sum. It's not a. Why you use the sum symbol to to put all the possibilities or all the permutations, okay, and in the sense that why you consider it is a sum? It's a sum in the sense that when two terms are the same, then one disappear because it is twice the same term, or what are the rules for this sum?
So the point is that if you think about relational semantics, you have these terms that are interpreted by sets, and the sum is the union.
Okay, the sum is the union. Okay,
And then this is because they don't consider really the coefficients here.
Yeah.
But in general, so for instance, let's still. So in general, in other more complex semantics, you can see can you see the screen?
Yes, I can.
Yeah, the interpretation of, so let's do the thing. So in the relational semantics, you have this, which is a subset of finite multisets of, say, A times B, right?
Mm-hmm.
So in this case, plus is just the union.
Okay.
But you can see this as a function from finite multisets of A times B into bool, right?
Okay, yeah.
So the idea is that you can do a weighted relational semantics where the interpretation of a program is finite multisets of A times B to R, which is any continuous semi-ring, okay?
Okay.
And this kind of thing is used to interpret probabilistic PCF or non-deterministic lambda-calculus,
Yeah, perfect. Yeah.
etc. And then the paper about quantum by Pagani, Selinger, and Benoit says, well, here you can go higher and put, rather than a semi-ring, a category.
Yeah.
Okay, and here I don't know the details, but
Yeah, but so the relation.
So the point is that a thing like this, you can see it as an infinite matrix, right?
Mm-hmm.
So you have here the bag, A, B, C, here the output, and here you can you have the coefficients that tells you, for instance, what is the probability of getting this output starting from this input. Okay?
Yeah, great.
But then the sum of the calculus means the sum of the two matrices. So the pointwise sum.
Yeah, nice.
This is a matrix, and you do the sum component by component.
Yeah, yeah, okay, nice.
If I remember correctly.
Yeah, no, that was really my question. So you answered perfectly. Thank you. Of course, I will look at the details later, but the another question is that do you know if the perpendicular lines lemma could be used to characterize the orthogonality between terms, in the sense that two terms are orthogonal if for all inputs they produce different outputs. You see?
Yeah. So good question. I'm not sure.
Because since okay, this is related with vector spaces, if you could have some characterization of orthogonal terms, then that could be used very well for quantum lambda calculus, where you need to
Okay.
ensure orthogonality to keep the norm of the term. And
Yeah.
I wonder, I mean, when I saw the perpendicular line lemma, I thought, okay, maybe that could be a
That's possible.
nice.
So yeah, I should think about it.
Okay. Okay, thank you. So, is there any other question in the audience? Okay, then we thank the speaker again. Thank you very much.
Thank you.
The claps is not working very well here, but you can see everybody clapping. And well, thank you very much for coming, and we will pay your
Thank
tickets
you all.
later.
I hope to see you in person the next time.
Yeah, me too.